Hi everyone, so today we're going to be looking at aromatics, which is our third lesson of this unit. So aromatics is very important because the most common type that we're going to look at is benzene. And benzene, the formula is C6H6, and this is a flat 6-carbon ring with a hydrogen atom that is bonded to each of the carbons. So you can see in the image there, but there is something called aromatic hydrocarbon, which is a ring structure and the bonding arrangement that allows it to be very chemically stable. So you can see there at the bottom that it is a certain structure. It's 6 carbon rings, and there are double and single bonds throughout. So when we look at the bonds throughout our carbon atoms, they are seen to be equal in length because the electrons in the bond are shared by all 6 carbon, and this is obviously referred to as resonance. And if we did not have resonance, the double bonds would be shorter than the single bonds, and the reason for that is because of stability. So 2 ways that we can name structures with benzene structures or benzene rings is the structure where benzene is the longest continuous chain, which is known as a parent chain, which is the one that we're most common with, but also where it is a substrate, and that is not the longest continuous chain that we had looked at. So when it is a substituent, then it is referred to as phenol, and we're going to see this in our examples later on, so do recall this term later. So when naming compounds with benzene rings, we have to follow the certain rules. So the benzene ring is the parent chain where our small alkyl group, which is the maximum of 5 carbons, and a non-carbon substituent, which is chlorine, fluorine, bromine, or iodine, are attached to the ring. So the rules are going to be as follows. So we're going to look for the one substituent, and if there's one, then we're going to name the group followed by that with the root name as benzene. And then if there's 2 or more, then we're going to number the carbon atoms to give the substituents the lowest position. And if 2 possibilities are available, start with the substituent that comes first alphabetically. So those are the 2 rules depending on how many substituents that we have. And it's very similar to what we looked at in the past, so it's just recalling these steps. So the following here are some examples. So the first example here, we have one substituent. So we label the substituent, which is methyl. And then because it has to follow the root by the root name, then we write methylbenzene. So that's all one word. You might see this also labeled as toluene, but methylbenzene is also the correct answer. And we're going to look at toluene afterwards. The next example here, so there's more than one. So if there's 2 possibilities, we're going to start with alphabetical first. So bromine starts here, and then we're going to go in the direction of the next substituent. So we're going to go towards chlorine. So we're going to name 1 bromo, and then 2 chlorobenzene. And then example 3 is a little bit longer, but we have 2 methyls here, and then we have 1 ethyl. So because of how it is labeled, ethyl goes first, so 1 ethyl. And then the methyls were on 2 and 4, so 2, 4 dimethylbenzene. This example here is also how we can label it. So we have a parent chain going on, but the thing here is that we do have a methyl, but we have this other shape here, and this is where we have our phenol that we talked about, where it could be a substituent. In this case it is. So because of that, we have to literally label and name it based off of where our substituent is. So that is how we name it. So based off of this, we look at the parent chain and we're going to number it based off of where our phenol is located. as well as where our substituents all are. So they are located around 3 and 4. And in this situation, we are just going to go from left to right based off of this because it's not alphabetical. So we're just going to name it from left to right due to where both our substituents are. And then we're going to do it alphabetical naming. Okay, so labeling is the same as always from left to right depending on what we're looking at, but because we have our phenol here, it does not matter. And then when we name it now, we have to go in alphabetical, and so because this is methyl, and methyl is on 4, we'll write 4, and there's only one of them, and then 3, and it's phenol, benzene. Okay, the next example here, same sort of thing. If this phenol was not there, does not matter. We are just going to label our parent chain. Does not matter what order, but one thing that we do have to take consideration is that this is a double bond, and so therefore that's why we start this is as 1. Based off of labeling, we have 6 phenol, and then because the double bond is on 3, we have hept 3 ene. Okay, so that is why we label it so. And then now we're going to draw the following. So we have A and B here. So we have 1 bromo, 2 chloro, 4 ethyl benzene, and then we have B, which is 4,6 diphenyl octyl 2ene. So we're going to label both of them. So A, we have 1 bromo, 2 chloro, 4 ethyl benzene. So because it's a benzene, we know the structure that it's going to be in. Obviously, your drawing will be better than mine. And then from there, we can label. So I usually start 1 at the top. Does not matter the order. And bromo is on 1, so this will be Br. 2 has or chloral. And then on 4, we have ethyl. So off of 4, we'll have CH2CH3. And then for B, we have 4,6 diphenyl octyl 2ene. So we know it's going to have a parent chain, and because it is oct, that means we know how many there are. So we'll have C all the way across. Okay, and then from there we can determine what our bonds are. So we can see it says 2ene. That means between right after 2 we'll have a double bond. So we figured that out. And then at 4 and 6 we will have we'll have 2 of our phenols. So at 4 and 6 we'll have 2 of those. Once again, your drawing will be better than mine. And then from there, we can label our bonds. So the remainder are going to be single bonds. We'll have CH3, CH, 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 CH2, CH3. Okay, so now we can look at traditional naming for aromatic compounds. So at certain locations, they can have certain prefixes. So some prefixes we're going to take a look at is ortho, meta, and para, and that is going to indicate the position of our substituents. So for ortho, you can see in the image on the left here, the substituents are found in the first and second position. If we look at meta and para, meta is at 1 and 3, and para is at 1 and 4. So these are the substituents at those positions. And that's all you need to understand is where the positioning is. There are some properties of aromatic compounds. So many are going to be seen as liquids at room temperatures, but others are solids. Most are seen as crystalline solids unless they have an electronegative substituent, which is attached as an OH or Cl. Because of that, they're impossible to dissolve in water. And benzene, just in typical everyday life, is used as a solvent and is used to clean clothes, but because it is now considered a carcinogen, it has been replaced by methylbenzene, which is known as toluene, which is what we've seen in the past few slides. So toluene you can see here because of where it is located and how many substituents it has. Toluene is something that is very volatile because it does evaporate and disperse into the air very easily. It is considered volatile. And that's all you really need to understand about toluene and the aromatic compounds. But we do have reactions that take place. So since the benzene ring is very stable, it does react differently than alkenes, and it's also less reactive than them. And what happens with benzene, it goes through a process called hydrogenation in order to create cyclohexane, and it requires high temperatures and a catalyst in order to do that. So here you can see that we have hydrogen being added to it, and in order to break that bond, so it's hydrogenation. Benzene can undergo substitution, which in reactions where the hydrogen atoms are going to be replaced by other atoms, such as chlorine in this case. And if we have hydrogen being replaced by chlorine, it does require a catalyst. So in this case here, we have our benzene, and where our hydrogen will be added, we now have chlorine, and our byproduct in this case is HCl. Also, we can have it react with HNO3, which also requires a catalyst, and if it does react with it, we have byproducts of NO2 and water as a byproduct. And then it can also react with chloromethane, which is, once again, oh my goodness, I apologize, that was hideous. It could create CH3 on that same spot, and HCl is a byproduct. So very dependent on what is going on in substitution reactions with our benzene. It does react like alkanes and cycloalkanes in similar ways because it does have very stable bonds. But as we know, with alkenes, it's not as stable. So with alkanes, it is very similar because of the stable bonds. And in both reactions, atoms are going to be seen as saturated hydrocarbons, and both undergo substitution reactions. So you can see here the byproducts, not only is our benzene with our chlorine attached to it, but we have HCl as also a byproduct. If we have our cyclohexane, which also undergoes an addition reaction, this is where our chlorine is added as a catalyst on top. And because of this, we break this double bond there, and no atoms can ever be lost. So what happens is we break that double bond, and therefore it is added across the double bonds, and it has a pull based off of electronegativity. So different things that can happen. Just do understand that benzene is similar to alkanes and cycloalkanes because of how stable is it, but it is very different than alkenes because of it is less reactive. And do understand what type of process it goes through. So it goes through hydrogenation, depending on how we want to undergo the reaction. So we're going to work on the following questions. In our textbook, this kind of messed up for some reason. So it's page 31, number 326.